Okay, hello everyone, and welcome to the session on freight and logistics optimization. My name is Jia Guo, and I'll be chairing this session. As we all know, freight and logistics are at the heart of global supply chains, and the optimization is increasingly critical in addressing challenges related to efficiency, cost, sustainability, and resilience. Today, we will be hearing from a range of presenters who will share innovative methods, data-driven insights, and applied solutions that contribute to advancing this field. Just a quick reminder before we begin. Each presenter will have a maximum of 20 minutes, which includes both their presentation and the Q&A section. Okay, now let's get started with our first presentation from Ying Sun. The topic is a modular multi-purpose vehicle routing problem with coupling and decoupling for collaborative passenger and freight transport. Welcome, Ying.
Hello everyone, I'm Ying Sun. The research I'm going to present today is a modular multi-purpose vehicle routing problem with coupling and decoupling for collaborative passenger and freight transport. And this is the outline of today's presentation. For the past 5 years, we can see a steady increasing trend of both the total amount of e-commerce and total passenger trips. Even if the COVID affected total passenger trips in 2020, we can see a quick increase again. And collaborative passenger and freight transport is proposed to deal with the evolving and varying demands of both passengers and freight. This collaborative framework emphasizes the integration of the two systems into a unified urban logistic framework, which can enhance the overall transportation efficiency. There are a variety of innovative transportation modes proposed for this system, as presented in the literature review, but the focus is mainly on reallocating vehicle capacity in existing public transport, such as the urban metro rail lines. And these proposed systems have common disadvantages, such as the inconveniences and security concerns associated with the space sharing between passenger and freight, and also the on-demand transport services have seldom been considered. A joint study on modularity and co-modality using an innovative vehicle concept, modular autonomous vehicles, namely MAVs, proposed a promising solution to these challenges faced by this co-model system. The modularity here involves two meanings. Firstly, MAVs are able to flexibly couple and decouple with each other as needed, and when coupled, these vehicles operate in close proximity, leveraging platooning effects with reduced energy consumption. And secondly, MAVs are internally configurable to accommodate passengers, freight, or other specialized demands. With such feature, MAVs can separate passengers and freight within the same vehicle, while simultaneously achieving both commodality and enhanced energy efficiency. There's an increasing number of studies for MAVs for the past 5 years, but the mainstream of these studies focus on deploying MAVs to the transit network with fixed corridors. Limited studies focus on the flexible routing of MAVs, and the flexible routing of MAVs implies a higher complexity in designing the MAV's coupling and decoupling tactics. Also, even few studies for the co-model transport system using MAVs are proposed. So the objective of this research is that, firstly, we want to design an on-demand co-model transport system operated by these modular autonomous vehicles. And secondly, we want to develop mathematical models to solve this problem, especially accounting for the routing and flexible en-route platoon configurations of MAVs in this system. And thirdly, we will devise efficient meta-heuristic algorithm that fits the problem feature and can solve large-scale instances. And finally, we will evaluate the performance of the proposed system and the design heuristics. Here I use a small road network to illustrate the system we investigated. The system has one passenger depot and one freight depot, a set of MAVs dedicated to either passenger type or freight type are going to provide services for customers of the same type. Note that the customer with negative demands request delivery service, while the customer with positive demands request a pickup service, and each customer specifies a service time window. There are some assumptions made for this system. The first is multi-visit. The system allows for multi-visit to a customer or a location, meaning that the MAVs can visit specific locations multiple times within the same trip. And as for the platoon formation, MAVs can couple to form a platoon at any node in the system, regardless of their different types. So to explore the platooning opportunities, we here propose two platooning mechanisms. The first is that the MAVs can wait at the location for the incoming MAVs, which will travel together along the same path. And secondly, the MAVs can take detours to make other MAVs along an alternative route. And as for the platooning benefits, the modular vehicles can take advantage of the platoon formation to reduce the energy consumption. To capture the coupling and decoupling behaviors of modules over time, the problem is modeled on a time-space network with a directed cyclic graph over a planning horizon. And three types of time-space arcs are defined, which are the moving arc, waiting arc, and serving arc. The time-space network is further refined by removing all the invisible nodes and arcs from the graph. The decision variables are evolved the following four parts, all of which focus on the operational level. The first is the routing of MAVs to serve each customer, and the second is the arrival and waiting time of each MAV at each location for each visit. And the third is the configurations of platoons, along with the locations and timing for their formation. And finally, the service load of each MAV in relation to the customers it serves. And these are the notations of the decision variables we considered. In terms of the objective function, it comprises the weighted sum of three terms. The first accounts for the total energy-related distance for all MAVs, and the second term considers the total trip durations of all MAVs. And the final term computes the penalty for a sub-request, and we consider different costs between losing one freight request and one passenger request using the parameter lambda. As for constraints, I will only highlight some key constraints that make our model different and difficult with others. So for example, in this page, the two arc-based constraints are formulated to describe the sequence of the moving arc, waiting arc, and serving arc, considering different time when a vehicle arrives at the customer and as well as the customer service time window. And the constraints in this page impose limitations on the waiting time at each location per visit, as well as the overall waiting time allowed throughout an MAV's route. The first two constraints listed in this page help configure a platoon on a time-space arc based on the number of coupled MAVs on that arc. To compare with, except for the main model, two benchmark models are also developed here, each featuring a distinct platoon formation strategy that differs from that of our proposed model. So benchmark model NC, representing no collaboration scenario, assumes that the platoons can only be formed by the MAVs of the same type. And the benchmark model NP, representing the no platooning scenario, assumes that no platoons can be formed at all. The next part is the algorithm. In our problem, we have two decision layers. The first is the sequence of the visiting customers, and the second is the choice of detour in order to explore the opportunities for MAV platooning. And this imposes some requirements to the algorithm design. First is a different representation for solutions. And second is to create new operators that account for the selection of detours between customers. And the third is a platooning heuristic designed to generate platoon configurations. So for the solution representation, we have two forms, which are the compact form and the extended form. So the compact form includes only the depots and the customers to be served, as well as the index of the detour between two adjacent customers. And in extended form, we will explicitly show the intermediate nodes traverse along the path between every two adjacent customers in the compact form. As no previous studies have jointly addressed the decisions of both the sequence of nodes and the path connecting the adjacent customer nodes, we propose two innovative approaches for this purpose. The first is the parallel approach. In this approach, at each iteration, the node-related operators and the path-related operators will both be executed. And the second is the sequential approach, that either node-related operators or path-related operators will be executed for a number of iterations and switch under certain conditions. Every time we obtain a solution by the hybrid ALNS algorithm with good quality, we will perform the platooning heuristic. We first build a pairwise visibility graph to check how a vehicle can be evolved in different platoons. Each node here in this graph represents a specific arc on a distinct position of the solution. And two nodes will be connected by an edge if specific conditions are met. With this pairwise visibility graph, finding the visible platoons will be equivalent to finding the maximal clicks in this graph. And the next step is to systematically find the set of visible platoons on different arcs as well as their specific departure time. And we do it in a greedy way. First, we find a platoon with the largest energy savings and remove them from the graph. And next, we update the departure time windows as well as the graph. And thirdly, and after updating the graph, there will be only one node left in this graph, which is not a visible platoon. This means that this algorithm comes to an end. In numerical experiments, we first use a small network to test the efficiency of our proposed model using the optimization software Groby. We compared the performance between the two benchmark models and the main model, and we can see that compared to the main model, the NC model has an objective value that is 2.1% higher than the main model, and the NP model has an objective value that is 5.3% higher than the main model. We further specify the energy-related total distance between models, and we can find the gap between the benchmark models and the main model is even larger. This indicates that the proposed model can effectively reduce the energy-related distance via the collaboration and flexible platooning. Next, we compare the performance between the parallel HALNS and the sequential HALNS, and we adopt the stopping criteria to be the 20 number of iterations without improvement. From the table, we found that the Groby cannot solve to optimal within 2 hours for networks with larger than 10 nodes and the planning horizon of 1 hour, which is 60 minutes. In contrast, both the parallel HALNS and the sequential HALNS perform much better than the Groby, indicated by the gap with the Groby. And CPU time for both HAL and S is less than 2 seconds for all the instances listed here. And I want to further validate whether the two algorithms perform similarly or differently. And we can see that both the algorithms perform similarly. Parallel HAL and S only beat sequential HAL and S in one instance investigated. The next experiments test the algorithms on medium to large networks. They are based on a network with 2-hour planning horizon. For Groby, it cannot give a feasible solution for all the instances investigated. So we want to have a straightforward comparison between the parallel and sequential HAL and S. After doing a t-test for both the objective value and the CPU time for the two algorithms, we can see that the parallel HAL&S performs much better than the sequential HAL&S in terms of the objective value, while not distinguishing much in the CPU time. Therefore, we use parallel HAL&S to study a real-world network, Anaheim network, and we randomly select 100 nodes as customers and select 2 nodes to be the depots. The other nodes are all intersections. The left-hand figure shows the process of convergence for the network with the number of iterations without improvement to be 500, and the CPU time is around 2000 seconds. And I also test the performance of the proposed system with this network. We can see that compared to the main model, the increase in objective value of NC model is 2.13%, while the increase of the NP model is 4.6%. This demonstrates the efficiency of our proposed model in this real network. So in conclusion, this study proposes a novel concept of a modular on-demand co-model transport system, and the MILP model based on a time-space network is developed to optimize the problem. And secondly, a hybrid adaptive large neighborhood search algorithm is introduced with different node and path operation strategies alongside an embedded platooning heuristic. And finally, numerical experiments are conducted to demonstrate the effectiveness of the proposed system and the proposed algorithm. This is the end of my presentation. Thank you.
Okay, thank you very much for your wonderful presentation. If you have questions, please feel free to let us know so that Ying is happy to answer your questions. Any questions? Or you can type it in our chat box. No, I have one question for Ying.
Yes.
So in your objective function, there is a term that is the energy-related distance. Is that right?
Yes.
So I'm kind of curious about how you calculate the energy-related distance. Is it just the distance, or did you take other factors into consideration, such as curvature or speed, or going up or down the hill into consideration? How did you get the value?
Yes, because we have this assumption in this model that the modular vehicles can take advantage of the platoon formation to reduce energy consumption. This means that for all the if several vehicles form a platoon, for all the following vehicles, they can reduce the energy consumption by 10%, which is referred to the relevant literature. So this means that here the energy related distance means that so the FH here is the energy saving ratio, which means that for all the following vehicles, they will have an energy saving of 10%. And we sum all the distance for all the vehicles up. And this formed the first term of the projective function, which means that
Yeah, go ahead.
maybe I can illustrate here. Okay, can you see? Yeah. So for example, the three vehicles form a platoon, and they will, their total distance is d. D is the distance that they travel together as a platoon. And for the first vehicle, I will count as distance to be d, but for the second and third, their distance will be 0.9 multiplied by d, because 10% of energy saving is assumed here. So this is the meaning for the first term.
I see, makes sense. Yeah, thank you very much for your explanation. Okay, thank you. Thank you very much for your insightful presentation. So next, let's move on to our next speaker, Xi-Chong Chen, with the topic of capacitated and time length constraint location arc routing problem with route partitions.
Okay. Okay, thank you, Professor Guo.
Thank you.
Yeah. Shall we start?
Yes, we can start.
Okay, let me share my. Okay, good morning or good afternoon, everyone. Yeah, I'm Chen Xi-Chong from Shanghai University, China. So it's my great honor to present our research titled Capacitated and Time Length Constrained Location Arc Routing Problem with Route Partitions. So today I'll walk you through 5 sections in about 20 minutes. So this is the first part, including the motivation and contributions. In logistics and transportation, many operations involve serving demands distributed over network edges. Think garbage collection, street wiping, and pipeline inspection. These scenarios are modeled by arc routing problems, so which inspired our work. When combined with facility location, ARP evolves into location arc routing problem, which aims to minimize systematic cost by optimizing depot, location, and service routes simultaneously. However, real-world operations often face additional constraints. Vehicles may exceed capacity or time limits middle route, so requiring intermediate replenishment or unloading. Existing studies on LARP and related problems like VRP either ignore these requirements or research on routing problems with intermediate facilities, which are usually specifically established with a limited specific function. And in most studies, vehicles are only allowed to enter the specific depot where it departs from. So our work stress this problem by introducing the route partitions. So that allows mutual use of opened depots for replenishment, making the model more realistic for large-scale, long-distance operations. So the proposed route partitions is a flexible approach to split the vehicle routes using open depots. Unlike intermediate facilities that rely on additionally construct intermediate facilities, route partition directly respond to constraints by dividing paths with the nearest open depots. So based on the above consideration, we proposed a new variant of LARP, that's LARP with route partitions. Our model operates on a directed graph with candidate depots, including real and dummy copies for partitioning, and a series of required arcs, which must be served. All depots have infinite supply or storage capability and enough vehicles as needed. So we need to decide which candidate depots select the number of open depots, which candidate depots will be opened, and the vehicles serving sequence for all the required arcs. So all vehicles need to start from a depot, serve some required arcs in sequence, and end up at the same depot. During the serving process, vehicles may pass through other depots to refresh their capacity or time constraints. So let's see in this solution case in the figure. Among all the 3 candidate depots, so 3 depots are selected to open. Vehicles are dispatched from these 3 depots to serve all the arcs. Let's take the vehicle from depot 1 as an example. So here, the vehicle departs from depot 1, serve arc 1, 2, 3, and in sequence, and then go to depot 2 for replenishment. Then continue to serve arc 4 and end its route at depot 1. So to establish the mathematical model of the problem, we introduced several sets of dummy depots, as you can see, dummy depot set 1, 2, and D, as intermediate depots and destinations. So which correspond, so this figure corresponds to the solution showed in this figure. So vehicles from 1, so 1, 2, 3, and to depot 2 for replenishment, and then serve arc 4, and then back to depot 1. So to formulate the problem, we introduced 3 decision variables. So which are all binary variables. The first one, YD, indicates whether candidate D is selected to open or not. So the second one is about allocating the acquired arc to the depot, and it takes one if required arc A is served by a vehicle K dispatched by the depot D. So the last one is for route decision, represent whether an arc is traveled by a vehicle K for depot D or not. So then we develop the objective function that minimizes the total cost, including 5 cost components. The first one, travel cost, including the service traveling cost and the dedicating traveling cost. The second one is about this depot establishment cost. The third one is about vehicle dispatching cost, and the last one is replenishment cost in intermediate depots. So the constraints are very variable. So the first one guarantees each required arc is served exactly once by one vehicle, and the second one vehicle pass through any depots at least as many as it's used for replenishment. So the next 2 are start and end depot constraints. So the next one is about total number of dispatched vehicles. So this part refers to the flow conservation constraint. And these 2 parts specify the value of L and T that's corresponding to the capacity and the time length constraints. So the last 2 parts are variable constraints. So the variant of LARP model has long been proven to be an NP hard problem. So we developed a multi-ant colony optimization to solve it. So this figure shows the framework of the MACO and employ 2 ant colonies to deal with the location part and the MDARP with root partition part, respectively. So the key ideas for this algorithm. So the first one, location colony used to select open depots using pheromone trails and demand to cost a heuristic. The second, solve the MDARP PR. So for given depots. So and then pheromones are updated to link both colonies to achieve global optimization. So this one is this procedure is for the location colony. We firstly generated the number of open depots by this equation, and which balances between high demand areas and cost efficiency. Then the ants use a probability rule to select the depots as these 2 equations. The other key process of MACO is about routing. So this figure shows the procedure. So this this ant colony optimization solves MDARP by first constructing a single network path that serves all the required arcs in the network with transition rules by shown equations. So then split the NST into feasible segments using insertion heuristic that check capacity and time constraints to generate feasible MDARP PR solutions. And then we use local search optimization to optimize the current solutions. When one ant finds a solution, local pheromone is updated for other ants. And after all ants from different colonies form their solution at each iteration, the global pheromone matrix is updated by the second rules. So global updates link both ants, ensuring local decision inform routing and vice versa. So next, we test 30 instances from public datasets with parameters, with informations like that. So we get the data source. We get the data source, and this the introduction of the instances. So we know the different types from the literature, the number of each experiment candidate set. This too is about the scale of the instances, and we add some other parameters to suit our model. So such as all these parameters. And this is preliminary experiments to calibrate the parameter settings for different kinds of instances. And then we compare the results of the different instances from Simplex and our algorithm. So as you can see, so the results shows very fast solution speed, and from the average and the best solution, we can see the stability of the algorithm and capability of handle large scale instances. So the efficiency, quality, and optimal gap for different instances. So the key findings of the comparison of different instances between Simplex and MACO, one is efficiency. MACO can solve all feasible instances in less than 123 seconds. So even with the scale large as 380 demand arcs. So while simplex struggle with instances with over 19 required arcs and took far longer for small instances. So quality deviation between MSCO's best and average solution range from 0.7 to 4.6, indicating stability. So the optimal gap compared to simplex, MACO's best solutions has gaps mostly between 1.88 and to 11%, with larger gaps in high demand cases. So as you can see here, the different symbols. This is corresponding instances undirected or connected and unsuitable for this case. And this one corresponding instance cannot be solved by simplex. So these are all the comparison results between the result of complex and our proposed algorithm. So let's go to the conclusion and prospect part. So we conduct the LARP-RP effectively models real-world logistics with capacity and time constraints. In our model, we consider the cost comprehensively, including 5 parts. And also we firstly proposed the route partition, which allows mutual visit for depots. And our algorithm is also provides efficient, stable solutions. So for future directions, we need to further enhance the heuristics, and also we need to generate larger directed graph instances for robust testing. And the last one, we may develop lower and upper bounds to better evaluate solution qualities in the future. So that's all for my presentation. Thanks, and questions are welcome.
Okay, thank you, Dr. Chen, for your wonderful presentation. So audience, if you have any questions, please feel free to raise your questions here or type your question in the chat box. Questions? Okay, I have one small question. So in the last slide for your future research direction, I'm very interested in you mentioned robust. To account for the uncertainty in your future research. So what kind of uncertainty you plan to include? Because it seems that your current your current research is pretty comprehensive. So I'm kind of curious what kind of uncertainty or undeterministic aspects you're going to consider in the future.
Okay, thank you for your question. So you mean which one, or just about our future direction?
Yes, just about your future direction, especially in uncertainty, because you mentioned, I remember you mentioned robust optimization, right?
Okay, thank you. So actually, I'm also very interested in the research of location routing problems on robust research. So for example, we can include in further demand, including the stochastic travel times, and not only further demands, stochastic demands also. For example, the required arcs, the amount of demand may vary, and also the exist of the required arcs also unsure. So we may research on that, including different kinds of uncertain variables.
I see. Yes.
But it's really complicated.
Yes, and these aspects are all worth investigation. So looking forward to that. All right.
Yes.
Do you have any other questions, audience? Oh, Dilip, you text execution time. Is it your question, or do you want to specify that? Yes. So I'm not sure whether. So Dilip, is your question about execution time? Yes. So I'm not sure because I don't quite understand this question. So Dr. Chen, if you,
For me,
if you understand it, and
so the execution time about this research or about our future research?
Philip, is about the future research or what?
Oh, you mean
about
my model? You mean the running time of the algorithm or the time I used to construct this model? I'm sorry. Oh, running time. Okay. So running time of the model show here. So for different instances, for example, the small, so this, so these are small instances. So so when the number here increases, the instances increase, the scale of instances the scale of instances increase. As you can see, the CPU time here for running this model, so we only use less than 10 seconds for all the GDB instances. And for other camps, for other types of instances, so the time is very short, very short. So we can see the efficiency of this model here, 40 seconds. For the largest instances, we only use 120 seconds for running this model. So for this model, as I remember, the required arcs should be increased to 100. So here you can see the simplex cannot get a feasible solution within this time, but we can run a result within this time, very short time. So the algorithm is very efficient for this result. Okay, thank you.
All right, do you have any other questions? No? Okay, then let's move on. Okay, thank you very much for Dr. Chen for a wonderful presentation. Now let's move on to our next presentation given by Sarah Sajadi Kha with the topic of presenting an approach for a safe replacement of hazmat along trains in marshalling yards to mitigate derailment risk. Welcome.
Hello, everybody. Can you hear me?
Yes, I can hear you.
So I'm going to share my screen. Do you see my screen?
Yes, I can see it.
Hello, everybody. Good morning or good afternoon. So I'm going to slideshow my presentation. Okay. My presentation title is, as you said, presenting an approach for a safe placement of hazmat material along train in marshalling yard to mitigate derailment risk. I'm Sara Sajadi Khan, and my co-authors are Mehdi Falahi and Dr. Martaza Bagheri. So, why rail transportation matter? Here is an introduction of my research. As you see in this slide, 53% of accidents are derailment that happened in rail transportation, mainly on marshalling yard because of the switching of the rail. It happens a lot, and according to TSB 2024 research, means B. Here's the pie that is shown. Let me see. And from the accident that happened in 2023 in Canada, 55 main track derailment has 10 hazmat material that are on the train that happened the derailment accident. And as we know, we can have a different type of hazmat material that if they are placed next to each other and derailment happens, it can cause maybe a huge accident and has a effect on environment, people's health, and goods. So, we are going to see prior works that they are has a similar subject to my research. Lin et al. That do his research on 2022 found front and rear wagons face higher risk using a hybrid analytic model, but it's limited to static simulation. And also Boré et al. In 2010 showed central placement reduced risk by 40%, yet lacked reinforcement learning integration. And also Pierre et al. Improved yard scheduling with DQN model through scalability was that scalability was an issue. And also Joe et al. Reduced cost by 17%, and also his model was VVPG, but focused on construction, not safety. Our study in 2025 used proximal policy optimization that we know by PPO to achieve risk reduction through validation for dynamic tracks that we dive into. So here's my methodology. Here's my risk model that I examine risk as my model that is P. It's and P is PATD is derailment probability, and POD is position probability of derailment, which is come from FRA data, and consequence that if we have hazmat material or if we have a non-hazmat material, it has a different consequence. That is, my consequence is a dollar value, and Y is if there is a hazmat or if there is no hazmat. As you can see, I have a matrix that we have A to F, different hazmat material. If in matrix, if we have one, the two kind of hazmat material should not be placed next to each other. And if it's zero, it doesn't matter if we place the hazmat material next to each other. And we have a group F that is do not contain any hazmat material, and it can be placed next to each of A to F, E, other hazmat material. And also, I have another rule that we should have 5 wagons that are buffer to our locomotive, that we cannot place any hazmat material on these 5 positions. So here is PTD on my research that is come from FRA data. As we can see, we can have a different cause of derailment, like roadbed defect, vehicle, and track geometry. And for a simpler study, I just see one cause of derailment in each segment that I'm going to explain next. So we have 3 blocks on my case study that contain block A, K, and C that are coming from the city that my train is going to visit. Block A has 25 wagons, 2 hazmat material, 1 type A and 1 type B. Block A has 13 wagons, 3 hazmat material, 1 type A, 1 type B, and 1 type C. And also Block C has 55 wagons that contain 5 hazmat material, or 1 type A, 2 type B, and 1 type C, and also 1 type D. And the track segments has I have 3 segments that are the distance between the city that train is visiting. Segment 1 has 100 miles. The track is class 2, and the train can goes to up to 25 miles per hour, and it has all my wagons 110. The train visit each city, and for example, in city Kansas City, the wagons and the blocks that belongs to the city are loading off from my train, and so because of that, in segment 2, I'm only gonna have 85 of wagons, and also in segment 3, because I'm going to load off 30 other wagons, I'm going to have 55 wagons left. And consequence, as I told you, it was dollar value, and it cost $1,100 if I have hazmat material, and $20,000 if I'm not going, if there is a non-hazmat material. And here is a map that my train is visiting Albuquerque, Kansas City, and Chicago at the end. If I'm going to explain my model implementation. Here is the flow chart of my code that I wrote. It's using a PPO algorithm of reinforcement learning that I'm defining environment that is contained of my case study, and my model is going to learn if a position is going to have a less risk or no, and it should check the constraint violation that I told you it was 5 buffer, and I have a matrix of incompatibility of some of hazmat material that my model checked that, and if it's um, if it's not if it's not sorry if it's checking all constraint violation, if there is no violation, my model going to save the optimization to my optimization train, and then it will show me the risk, the time, and the position of each wagon, if there are hazmat or if there are non-hazmat. So here's my result. As I told you, my train has 3 blocks, and if it's going to place a different kind of block at first, at second, and at the end, it's going to have a different risk, as there is shown to you. Block the placement of BTR has less risk value as its dollar value. And as you can see, there is a position of different hazmat material, which are type A, type B, and type C, and type D in different block in my train. So I'm going to go to next slide. For the validation and sensitivity analysis, I describe parameters on my reinforcement learning PPO model. I check different value for each parameters and best value for every parameters. For example, learning rate and gamma and coefficient are as they are shown in this slide and in this table. As the result, 10% we have 10% increase in hazmat wagons. We will have 50% risk, and if we are going to validate my research, I do a similar small train which has 20 wagons, and also the risk of, for example, COSIA was $185,100. And also, if we use a PPO optimization wagon placement, will be reduced risk by 30%, as if we place randomly a train of 110 wagons. So there is my results, and for future work, we could have extended model to dynamic track condition and larger fleets, and also we could see loading in each segment of stations For example, I just see losing of wagons, or in each segment we could also see loading of wagons too. And so here's my references. As you can see, thank you for your attention. I'm available to answer your questions. If there is a question, feel free to ask.
Thank you very much, Sarah, for your insightful presentation. If you have questions, please let us know, or you can type it in the chat box. Okay, I guess audience.
I have a quick
Yeah.
question. Sorry, I have a quick question. Thank you for your great presentation. So
Thank you.
based on my understanding, you're using PPO to minimize the risk here. So may I ask your state vector and action vector in this RL setup?
Can you ask your question again? I
Sure.
didn't hear it.
So I'm asking about your state vector, your input of your model in this
Yes.
PPO reinforcement learning setup.
My input parameters was my case study parameters that has I have some type of material. I have a number of blocks, number of wagons. These are my inputs that are defined in the environment of my model. That my main code was learning the environment, which has my case study, and it's learning that. If I understand your question correctly, that was my input.
Yes. And may I ask about your action set as well? So the RL agent is doing an action. And
Yes,
yeah.
yes. The action was changing the wagons that is going to examine the risk value. If it has a better risk, the action chose the position that has less risk from the previous learning that it was saved.
Yeah, thank you very much. Yeah.
You're welcome.
Any other questions from the audience? Oh, I have a question. So
Yes.
in your results, you said there are different types, like type A, type B, and type C. Maybe I missed
Yes.
something. Could you give us more explanation, details on what type A and B and C refer to?
Here is the incompatibility matrix that my model learned from. I said that I have a different kind of hazmat material. They can be type A, type B, type C, type D, and type E. For example, some kind of wagons in a train, they have a cooling system, or they don't have it because there are different type of hazmat material. And some of wagons, for example, type E has a cooling system on it, and type D is not having that. Because of that, some kind of material that are chemically not shouldn't be next to each other. For example, A and B chemically shouldn't place next to each other, and it's going to have a one. My model sees if there is A or B in that wagons. The model don't place those two wagons next to each other, and at least it must have one buffer between the A and B.
I see. I understand. Thank you very much.
You're welcome.
Okay, any other questions? Okay, if we don't have any further questions, then thank you very much for Dr. Sarah for your wonderful presentation. And then in the interest of time, I will proceed to our next speaker, Dr. Dilip Raut. And the topic is a cost-effective and efficient procedure for distance measurement of hotels and estimating influence of detour on pricing. Welcome.
So, good morning and good afternoon, Dr. Jia and other members available here. My name is Dilip Raut. I'll be presenting our work, a cost-effective and efficient procedure for distance measurement of hotels and estimating influence of detour on pricing, with my students Rajasri, Raman, Sneha, Anup, and my collaborator, Dr. Saukat. So this is the outline of our presentation. We'll be going for introduction, then literature survey, and what methodology we have done. Then we'll be presenting our result and some kind of analysis, and then we'll conclude. To start with, tourism is one of the aspects where it is also contributing to the GDP, let's say a kind of 10% according to the survey in 2019, and also gives an opportunity for employment and development around that place where the tourism is promoted. And in the tourism, there is distance plays a crucial role because of accessibility and all. Then in that, the geographical coordinates as well as the transit stops that is possible, that is railways or airports, those matters. So our problem statement is about given some of the coordinates of the transit hubs like airport and railways, and also some of the hotels that is available. And then what we need to do is first find out the distances. Distances we mean the road distances. Then we know the pricing of the hotels, and those pricings are collected from various websites like booking.com, Make My Trip, etc. And we are trying to find out whether there is a relationship between the distance and the pricing. So the objective is to find, compute, and verify the road distances. It means that we have applied two different kind of um, approaches to find out the road distances, and we are verifying each other cross verification. Then we are analyzing whether the aerial distance and the road distance of the hotels are varying too much, or is there an impact on that, and also the demographic one. If there is a impact on the demographics based on the city location, its altitude, etc., if there is a impact on it, so that we are trying to find out. And our hypothesis, there are a couple of hypotheses developed as per the suggestions from the reviewers. So we're trying to find out whether the Google Map, one of the uh, APIs we have used to find the road distance, as well as we have gone for open state route map. So we're trying to find out whether the Google Map is giving always a shorter distance than the OSRM, or the reverse in the hypothesis 2. Then hypothesis 3 is that whether the shorter distance or shorter detour distances are having a higher price of the hotels. Then we're also trying to find out if the road distance is a better predictor than the price than aerial distance. So we'll be trying to prove those. Then we have certain assumptions, like we're calculating the distances when there is ideal traffic, that is no traffic around midnight, and the uh, travel is about we're traveling in a car, so that's why how we are just calculating the distance. Then it is a hotel price depend on the website policy. So what we did it, we have collected from multiple websites. Some of the hotels are repeated in some of the website. So in that case, we have taken the minimum price of the hotel because it is the dynamical price is there. So we have collected and settled down it. Contribution wise, we are designing one procedure which is cost effective. That means we do not have to go physically there. Still, we'll be having an estimate of what is the road is approximately some distance and can use some API services, and we'll be also demonstrating that it's not just about using the API services directly. Rather, there are some tweaks we have to do to collect actual shorter distance that is by road. So we have, of course, this will be internet based, and we have for cross verification of our distances or the measurements, we have used two directions APIs, and particularly the Google Map API and OSRM API, the direction service. So we have used that one. Previously, we used to have the distance matrix, but it didn't work. So going ahead, then we're having the another contribution that actually we have applied this into two different Indian cities, Bhubaneswar, that is in Odisha, Aligarh, that's in Uttar Pradesh. The reason for adding those is these are tier two cities, which are upcoming in India in the list of smart cities. So in the Bhubaneswar city, basically, it's not having a different kind of terrain or altitude is not so high. But in case of Aligarh, you'll find a lot of hilly areas. So that is altitude is a little bit high. So that is why we have taken two different zones. And Bhubaneswar is located in eastern India, whereas Aligarh is located in northern India. So we are also trying to find out that how the correlation happens in case of detour, that is deviation distance to the road distance on the hotel pricing. And there are some methodology we have applied. And in the literature, as we have talked earlier in the introduction, that hospitality industry is actually influenced by the location and accessibility. And some of the machine learning and GIS systems can be used for the dynamic pricing for optimized pricing. And distance is also one of the crucial there. And not only the aerial distance, road distance, somewhat matter. And um, calculation wise, Google Maps API and open source routing machine, that is OpenStreetMap API. So both are used in the real world applications. So we have a couple of research questions over here, whether the accessibility quantified and incorporated into the pricing strategies. Also, the existing study primarily relied on aerial distances, though there are some discussion on the road distance also. And there will be some network variation, detour also. Then, so the aerial distances actually can be kind of 15% or to 40% lower than the road distance. So it may affect it. So that we are going to test it. So that's why we are proposing a model which is considering the detour. And this is without the physical verification. Still, we can find a good estimation using the API services available on the internet. So coming to the methodology, this is speaks about our complete workflow where we're starting and we're collecting the data from several websites, and we are trying to have the uh, hotel pricing, one day hotel pricing. Then if there is multiple sources which is giving us same hotel, then we're taking the minimum pricing. Then we're having calculation. Sometimes we're checking manually that whether the location is good or not, so where if we need some adjustment. So with the hotel name and with the coordinates, with the Google Map, we're trying to again fix those couple of errors. Then we have find data. Then we're computing three things, that is aerial distance and on-road distance, as well as on-road distance on OSRM, as well as on distance on the Google Map. So finally, we are validating it by cross-verifying each other. And also, as we know that aerial distance should be minimum. So that is how we are also trying to validate the data. Then after validation, we are having a synthesized data which is having aerial distance, on-road distance, as well as price. This is our basic fundamental variables where we are trying to propose our hypothesis. Then we're applying some pair t-test, correlation coefficient, and some of the visualizations like histogram, scatter plot to prove our hypothesis. Then what are the different factors affecting those, that the transit hub distance effect, then detour effect on the influence of the transit hubs. So this is our sample data where we have taken two hotels, basically 1, 2 are hotels. Then we have our transit point, that is airport on both the cities, Aligarh and Bhubaneswar. Similarly, railway station in both the cities, that is Bhubaneswar and Aligarh. Then we have their latitude, longitude, and the prices of the hotels are given. So in total, we have collected kind of 712, including both the cities, which are also one of the comments. So coming to how we are calculating the distance through OSRM API. So we're loading the input data, that means the coordinates of the hotel and the transit hubs. Then if there are missing coordinates, we cannot propose it. So one by one serially we're calculating, then construct the URLs, and with the HTTP services, we have just extracting the different distances, on-road distances using OSRM map API, and we are on the output we are getting a JSON file. Again, from the JSON file, it is not human readable. So from that, we are converting that into a Python dictionary where we can export it into a Excel file or CSV file. Then we're trying to find out if the root key dictionary is empty or not. If empty means, it means that it cannot extract the different paths of the route. Then if that is there, then we are selecting the minimum, because for one source and pair on road distance may be giving you multiple routes. So as many people might have used Google Transit. So we're exporting those into a file, CSV file. A similar thing has been done in Google Map as well. After loading that, we are constructing API request. And let me tell you that there is a limit on the API request that you can make per day if you are using a free service. Then from which API? So we have used particular directions API. So if the response code is not 200, uh, 200, sorry, 200, then we're sure that we are getting some kind of output. So we are again getting a JSON file that again we're converting to a JSON file into a Python dictionary. Then we're again computing the minimum path. So that minimum path we are saving it. Otherwise, there is an error. Okay, so the verification for purpose, we have used PR test, which is very simple between OSRM and Google Map API distances. Then we have also used a differential rain cloud visualization. I'll show that in a couple of minutes, a couple of seconds. So after that, we have used also Pearson correlation matrix, which is about the with the mean, how much deviation is there and what is the maximum deviation we can have. Then which will vary, the output will vary from -1 to 1. So other data visualization also you have used, and particularly we have used heat map for showing the correlation. And coming to the result part, so this is the difference that we are going to make. So if we are combining all the railway station distance to the hotels, including both the cities, this is how it look like rain cloud, differential rain cloud. Then in that case, we have some scattered points that you can see that the points are varying if you are differencing between OSRM and Google Map. Okay, that distances. Then it is varying from kind of 15 to 30. Okay, so minus 15, 30. So again, in this case, this is a box plot, which is showing that railway station distances are compact and not much differences. And in this case, you can see that there are a little bit errors in that, outliers in that. That's why it's not looking like a normal curve. On the other way around, if you look at the difference in the airport, so these are also scattered, and this is, but the deviation is more. I mean, the uh, first quartile to third quartile, the number of points are less in comparison to railways, and but it is looking more like a normal curve. So that will come to that. So in the scatter plot, we can have the -10 to 10. Majority of those are having it in both the cases. And railway stations tragedy hub are more compact than airport, that way I told. And some of the in the histogram, some of the spikes are given in the uh, airport, more spikes than the railway station. So coming to the pair t-test results, that we can see that in this case, airport, we fail to reject the null hypothesis. That means difference between the OSRM calculation and Google Map calculation both appear to be same. And in case of railways, it has rejected the null of it. There is some difference, but there's maybe a impact of outliers. That is why maybe that is the result that we got it. So that will still trying to figure out to make it better. And if you look at the airports in both cities and we try to plot how much detour that we can have in case of Bhubaneswar, we can find out the detours, number of detours are less, the variation, the dispersion of the detours are less, and you can have in Bhubaneswar we have more number of hotels. In fact, so in case of Aligarh, we have a lot of variation in that hotel detours. That means deviation from the actual aerial distance, and it may be the Aligarh, maybe it is having a different kind of terrain which is impacted by the altitude. That's why probably it is having some diversion like this. So if you just compare the distances, so the detour with the price, the scatter plot looks like this, and the relationship in the Bhubaneswar plot, you can see that it's not very high, although some exceptions are there. But in this Aligarh, you can see that with the less distance, the pricing is a little bit higher. So it may be due to the altitude, we assume. So in case of correlation matrix, we see that some of the negative correlation has been happened with the pricing and the detour if you just compare. And in case of distance and detour, if you compare, then we find that the detour is having more impact on that, okay, more influence in pricing. So this is how we end. And coming to the hypothesis, we didn't find all the hypotheses, first two hypotheses, that means none of those are greater or smaller. Exactly, we cannot say that monotonyically. So that is why those are false. And yes, we find that the shorter distances were having little bit significant higher prices that we may have to test it one more time or more rigorously. Then road distance is a better predictor, yes, than pricing than the aerial distance if you compare. Then with the lower price, mostly better connectivity and ease of access, people are preferring some of the hotels that we understand from this study. And there is a effective road network and impact of hospitality industry. This is one of the key factor also in urban development. And there is a very limited correlation between, as we have seen the correlation matrix, but still we think that there is some influence of the detour if you deviate from the aerial distance. And also there is a matter that some of the amenities, service quality, and local demand pattern also may influence the hotel pricing, which will be including in our feature research. And also some of the machine learning techniques where we can predict it, we can apply for predicting those models pricing depending on various various features on that. Then additionally, geographically, regions may be incorporated, like we have a little study on altitude, etc. But maybe some of the other factors maybe we can consider in our future research, which will be also impacting the tourism, or mainly the hotel pricing and choosing the hotel by the people. Maybe the comment on the ratings also. Yeah, we may have to incorporate the user rating. That's maybe influencer, but we have to also consider that how much impact the distances are making also. So with that, I'd like to thank everyone and will appreciate if any kind of feedback may be given. Thank you. Over to you, Chair. Yeah.
Thank you very much, Dr. Dilip, for your insightful presentation. Audience, if you have questions, please feel free to let us know. Yes, some audience are typing their questions now. I have a question. Maybe I missed something, Dr. Dilip. I have a question. So I thought in your computations, there are only 2 hotels, right? However, page, yes. However, on page
I'll
17.
request. Could you be a little bit louder? So it's.
Sorry.
Yeah.
Yeah. So I thought in your experiments you have only two hotels, right? But on page 17 of your slides, I see there are a lot of points in the scatter plot, and also page 19, I see the sample size is more than like 700. So I'm kind of confused about where each individual sample comes from. So that seems contradict my first understanding of only two um, two hotels and two airports and railway stations. So could you explain that?
Right. If I am getting the question right, all this scatter plot, different plotting that you're asking, why you have
Right,
plotted so much? Yeah.
Yes.
So we were showing the same hypothesis that whether there is a difference in two cities.
Mhm.
Also, if there is a difference in two API services. So
Mhm.
for that, we have different kind of plotting we have applied to test the same hypothesis. First one is, let's say, is there a difference in two cities? As we have observed in case of some of the observation in Bhubaneswar and Aligarh, yes, there is a difference in two cities. Aligarh is behaving a little bit different than Bhubaneswar, and suppose, for example, we can conclude that if you are moving the same distance in both the cities, you find that in Aligarh the pricing is a little bit higher. So that's what we can conclude. Then the second one is about the OSRM and Google Map, and there is nothing shorter in that. Monotonically, we cannot assume that both are giving. I mean, one is particularly better than other. It's very difficult to conclude, but yes, they differ at some point of time. That we are sure. So that we have proved with the pair T test, and we found that yes, they are differing in case of railway station distances, not much difference in case of airport. But we are still figuring out more cities and more kind of hotels to prove it because the sample size we have taken so far is 712. So we will like to improve it to something like 2000 or something so that it will be a good concrete evidence for that. Yeah, that is our
I see.
future. Yeah.
I see. Thank you very much for your clarification. Audience, do you have any other questions? Okay, then thank you very much, Dr. Delep, for your wonderful presentation. I think two of our presenters are missing today, right? So if you're in our meeting room and still haven't and plan to present but still haven't presented, please let us know so that we'll make you a co-host. Is there anyone?
Yeah, thank you all. Yeah.
Thank you. No? Okay, then this brings us to the end of this session on freight and logistics optimization. I'd like to sincerely thank all of our presenters for their valuable contributions and thought-provoking discussions. And thank you all for attending and engaging. I hope you found the session insightful and enjoy the rest of the conference. All right, thank you.
Thank you very much, Dr. Jia.
Thank you. Thank you, Nazar.
No worries.